welcome back to our channel. Today we're going to be reviewing some high school problems from TrinMaC Virtual Winter 2020. If you have any questions at all, please put them in the comments below and we'll be sure to respond. If you liked this video, please subscribe. Alright, let's get into it.
For the final session, basically we wanted to talk about basically some of the problems that we've written for some past competitions, some solutions there, and then maybe a sort of like a little insight into how we came up with them and that sort of process. Um, so first up is this one. So basically the question is, you're given that x squared plus 10y plus y squared equals y squared plus 6x plus 16, and you want to find the minimum value of x squared plus y squared. So this is the one that's from the most recent competition. X and y are real numbers here. So I know it's a team competition, so maybe not all of you have thought about this one before. So you'll give like a couple minutes kind of just to think about it. And then we can talk about some approaches, maybe some hints along the way. And then we'll share the solution, of course.
Yeah, I guess we can also just give a hint. You can think about trying to use factorization. I think like the idea here is like we should try and use factorization. And if you've taken, I don't know, like an algebra 1 or this shows up maybe geometry class, if you can think about just like what does x squared plus y squared, like have you ever seen that sort of form in any like geometric sense?
Yeah, for sure. So I would try and think about sort of factoring this in a clever way, and seeing when you get there, seeing if you can come up with any sort of like geometrical interpretation there. And then likewise for x squared plus y squared, if you've ever seen x squared plus y squared interpreted in a sort of geometric sense. So here we basically put all the variables on one side instead of instead of the x and the y. We like completed the square, so you factor these as squares, and then basically when you add this to the other side and then square root, then you have this sort of absolute value equation. So once you have this equation, then what you can do is graph that. So the graph of that, essentially, if you're not familiar with like absolute value graphs, then basically what's going on here is you can essentially say that like you're kind of dealing with different plus minuses. So like essentially one of the lines here is when it's a plus, and one of the lines here is when the slope's a minus, because absolute values can be sort of just thought of as a plus and a minus sometimes. That's an easier way to think about it. So wait, here we go. So then basically once you know the graph of the given equation, the whole like x squared, y squared, and 10y and all that, once you know it looks like this, then our idea was to interpret x squared plus y squared essentially as a circle. So in case you guys aren't familiar, the equation x squared plus y squared equals r squared, where like r is some constant, this is the equation of a circle of radius r centered at the origin. And the reason for that is because you can imagine it being like this, x minus 0 squared, it's the same thing, plus y minus 0 squared equals r squared. And then if you square root both sides, then on this side you would have the square root here, and on this side this little squared would go away. And then if you're aware of the distance formula, what this is effectively saying is that the distance from the point x comma y to the point 0 comma 0 is r. And that's exactly what the sort of English definition of a circle is. Kind of like a circle is essentially all points that are a radius away from the center. So this, all of this is to say that you can interpret x squared plus y squared essentially as, you can draw like the circle here basically you want to draw the circle of minimum radius, so that it's just barely touching this graph, but not so much so that it's like intersecting at multiple points. That's why it's the minimal value. And then basically with some like 45, 45, 90 triangles, you can figure out that this radius is root 2. And then remembering that x squared plus y squared is not the radius, but the radius squared. If this is root 2, then this will be root 2 squared, which is 2. But let's move on to this problem. So we're hoping to find the sum of all positive integers n such that the floor of n squared over 5 is prime. In case you haven't seen the floor before, basically just it means like the integer that's sort of like right below where you are. So like basically take your number, chop off the decimal part of it, and then that's the floor. So like the floor of 3.1 is 3, and the floor of 5 is 5. So like the floor of an integer is the same. So yeah, so basically take the decimal, chop it off, that's your floor. A hint, I would direct your thinking in like mod 5. Then you can write n as basically you can say n is 5k plus some remainder. So basically you could say it's 5k plus 0 or 5k plus 1 or 5k plus 2, and so on up until 5k plus 4, right? Because basically every single number can be thought of as basically being divided by 5 and then having some remainder from 0, 1, 2, 3, or 4. I guess I should write this out. So I would try thinking about like if n is like one of these forms, what does the floor simplify to? Or this expression, what does it simplify to?
I think also like when you see like this is like a general strategy tip, but like when you see something with like all positive integers n or find the sum of all positive integers, like in some sense like there is only a finite number for the most case. I could see like a lot of cases where it's like like geometric series, like it pulls out to be that, but like if usually like the answer is like a finite number of terms, you can figure out what doesn't work and try and like show like everything except this works. Try and figure out the lesson.
Here is basically I said 5k plus the remainder, just to make sure that k is like a positive integer and not potentially 0. I just recommended that you test 1 through 4 first. So basically when you test 1 through 4, you can see that 4 works because you'll get 4 squared is 16 divided by 5 is 3 point something. So then the 4 would be 3 and 3 is prime. So the first 4 numbers, 4 works. And then basically for n greater than or equal to 5, you go into this casework depending on what n is mod 5, right? So the first case is when n is a multiple of 5, so the remainder is 0, which means that n can be written as 5k, where k is some positive integer, and n denotes the set of positive integers. So if you just plug in n equals 5k into the expression here, you get 5k squared over 5, which is 25k squared over 5, which is, if you write out the steps a little bit more, you'd see it's the floor of 5k squared, but 5k squared is an integer, so the floor of 5k squared is just 5k squared. The floor of an integer is itself. So basically, the reason that we're going into this casework is that the 5 on the numerator oftentimes helps cancel with the 5 in the denominator, allowing you to get rid of the floor and just deal with an actual expression as opposed to like weird floor things. So once you plug this in, you get 5k squared. So the question is, okay, when is 5k squared prime? And that's obviously when k is 1, right? Because if k is like 2 or 3, then like we'll have k as a factor. So it's only prime if k is 1, which goes to show you that n equals 5 is a solution, which someone in the chat said before. But not only do we know that 5 is the solution, we now know that any number that's of the form 5k, so in other words, any multiple of, for all multiples of 5, The only one that works is 5. And likewise, we're going to do similar logic here. So now we're going to say, we're basically testing with this algebra, we're essentially testing every single number that's 1 mod 5, every single number that leaves a remainder of 1 when divided by 5. So those numbers are of this form, 5k plus 1. Very similar logic. You expand out the square. You get this. What happens is when you distribute the division, this becomes 5k squared, right? Because of 25 divided by 5. This becomes 2k. So 5k squared is an integer, so that comes out of the floor. 2k is also an integer that comes out of the floor, which is why you see it here. And the reason the 1 vanishes is because basically what it's adding is it's adding a plus 1/5. It's like adding like a 0.2 to your number. And remember that what the floor does is it essentially chops off decimal values. It chops off things that are basically fractional, less than 1. So this plus 1/5 goes away because of the floor. So what you're left with is just this part divided by 5 and this part divided by 5, which is 5k squared plus 2k. And then you can obviously factor the k out. And then this can only be prime if k is 1, because otherwise k would be a factor. And you do test it that you end up getting 7, which is prime. Then you, if k is 1, that implies that n is 6, because we said n is equal to 5 times k, or 5 times 1 plus 1. So that shows you that 6 is still a solution. And again, as I said before, we're not just saying that 6 is a solution. It's not like we just plugged in 6 and got 6 as a solution. With all this algebra, we're showing that for literally, like for any number that is 1 mod 5, all infinitely many of them, the only one of those that works is 6. And then basically what we do is we repeat this process for each mod 5. And there's obviously 5 of them. So we did it for 1 here. We did it for 1 mod 5 here. This is for 2 mod 5. So in this expression, you end up getting something that's never prime, because if you plug in 1 here, you get 9. So that doesn't end up working out. And then likewise logic here. So you just plug in case 4 and case 5, and you do not get any more answers. So basically only ones that worked was 4, 5, and 6. So you add those up because they wanted the sum, and you get 15. So basically the key idea here was to think about everything mod 5 so that the floor disappeared, which allowed you to think about the primes more easily.
Also, if you are not so familiar with like mods, like that's something we just somewhat like glossed over just for the purpose of this. You can also just like go to the YouTube channel. I think from TrinMaC Camp, we talked a little bit about modular arithmetic in one of the sessions. So yeah, that would just be like, it's a very useful tool in these math competitions in general, but also just like any sort of number theory problem like that they could come into play.
So yeah, let's go on to the next one. So this one definitely obviously very trig heavy. So you're given that sine to the 6th theta plus cos to the 6th theta is 11/12, and you're hoping to find the absolute value of sine 2 theta. Yeah, I mean for these equations, I mean it's similar to the first one in that whenever you're always like given this expression, find this expression, you never want to solve for any variables. It's always about just trying to manipulate what you're given.
Again, yeah, a hint would be like Prakash provided the hint that you should think about how you might like manipulate, but of course, like we're dealing with trig here, so like trig identities will be very useful.
Yeah, maybe I'll write down some ones that I think could be useful. Sine squared x or theta plus cos squared x equals 1. That's basically like Pythag. And then the other one that's probably going to be useful is the double angle formula, which is this one. So those two should be helpful. Just in case you feel a little bit lost, like a further hint I would say is with this equation, try cubing this.
And I would just use like binomial theorem for that.
Yeah. So if you know the binomial theorem is, then use that to expand this term. If not, you can, I guess, multiply some things out because it's, I guess, pretty low. But yeah, I would recommend taking this equation, try cubing it, and see what you get from there. Shaman, do you want to go through it then?
Sure, thank you. Upon looking on this, we see if you were to allow, just for the sake of simplification, I'm going to let x equal sine of theta squared,
Okay.
and I'm going to let y be cosine of theta squared.
Mm-hmm.
If this is the case, then our equation is x cubed. Sorry, my mouse.
If it's easier to type it, that's also.
I know. I just prefer writing. I think it's a lot cleaner.
Okay.
Plus y cubed is what we get over here.
Right.
With that, this can factor into x plus y x squared minus xy plus y squared. At this stage, we can use this trig identity
Yep.
to realize that this is 1.
Yep.
And we get x squared minus xy plus y squared equals 11 over 12. Xy happens to be, sorry, give me a second. Xy should, the square root of this should be equal to this. No,
The
please.
square.
Actually, I don't think I'll be able to get my solution done on time. If it wouldn't be
Okay.
an issue.
Yeah. There's 50 seconds, but I like the direction of this a lot. The sum of cubes is very good. X plus y equals 1 is a very good observation.
I think it's
because
similar to our solution, right? It's just like a slight different manipulation.
yeah, it's very, very similar. So it's just like a few seconds left. I'll just present what we have. So basically, it's exactly what you said. You take this equation, you cube it. So then this is just basically by the binomial theorem. And then you can just kind of factor some things out. So this becomes 1. This is basically the x plus y equals 1 thing. And then from here, because 1 equal, this is 11/12, so you know that this component is going to be 1/12. So you know that, so then from here, you get to